Predicting the future is an important part of designing an artificial driving intelligence. It allows us to evaluate the quality of a given action and reason about scene dynamics, predicting how other pedestrians and cars will act around us. Current approaches are typically unable to accurately estimate multimodal uncertainty and predict the stochastic nature of the future. Systems that can are often not differentiable or end-to-end trainable, meaning that they reason over hand-coded representations. They often predict the behavior of each actor in the scene independently and rely on an HE map to predict the static scene. This fails in many multi-agent interaction situations or with HE map errors due to word works, for example. We present a new framework that is able to overcome these shortcomings. It allows our end-to-end deep driving policy to explicitly reason about the future. We predict the future semantics, depth, and flow of complex real-world urban scenes. We demonstrate that our probabilistic model is able to generate visually diverse and plausible futures. And finally, we showed that our future prediction representation substantially improves a learned autonomous driving policy. Let's now dive into our model. To predict the future, we must first understand the past. Using a perception network pre-trained for symmetry segmentation, depth, and flow, we extract compact perception features from past RGB video frames. Our dynamics model then combines spatio-temporal information from the scene. The proposed architecture learns hierarchically rich features with both local and global spatio-temporal context. From this representation, we can decode future perception outputs. We don't have access to the true scene labels, but we can generate pseudo-ground truth labels from our pre-trained perception network by decoding the actual future RGB frames. Our loss penalizes our predicted segmentation, depth, and flow with respect to the pseudo-ground truth. However, as it is, the model is deterministic. Therefore, even if it predicts a plausible future, but one that happens to be different from the current training sequence, the training loss will heavily penalize our prediction without any proper way to take into account the stochastic nature of the world. To account for this, we introduce a novel method to model the future in a probabilistic way with a conditional variational approach. Our network additionally parameterizes two probability distributions, the present and the future distribution. At training time, we allow the model to have a privileged view of the future for the future distribution. As we cannot see the future at test time, we train the present distribution using only the current state to match the future distribution through a KL divergence loss. We can then sample from the present distribution during inference when we do not have access to the future. We observe that this paradigm allows the model to learn accurate and diverse probabilistic future prediction outputs. Finally, our future prediction representation is the input to learn autonomous driving policy, the control module. The present distribution network P learns a probabilistic encoding from the current state ZT. This distribution must capture the diverse possible futures that are likely from the particular state. To train that network, we use a future distribution network F that has access to a privileged view of the future, along with a mod covering KL divergence loss. Three key points were necessary for this probabilistic future prediction framework. The first one was to predict multiple steps in the future, in our case 2 seconds, as it's extremely hard to capture the probabilistic nature of the future, but only predicting one of the few steps in the future, like previous works, given how correlated the first frame of the different possible futures are. Next was the diversity of the training data. If the training set does not contain diverse futures, the present distribution will not be able to capture the different modes of the future. We trained our model on 200 hours of urban driving data. And finally, the training process also relies greatly on how the network is able to learn an abstract state to representation ZT that is invariant to irrelevant changes in appearance for similar high-level behaviors. That is made possible with our framework that does not rely on pixel encoding, but instead encodes motion, semantics, and geometry into ZT. Now let's have a look at our results. We compared our model with our proposed temporal box spatio-temporal module, which is a 3D convolutional module with both local and global features, to the following baselines. No temporal module, called static, and other spatio-temporal modules such as convolutional GRU, 3D separable inception, and so forth. And we see a large improvement of both perception, that is to say segmentation, depth, and flow, and control metrics, steering and speed. Next, we evaluated our future prediction model on cityscapes and compared to the previous state of the art, predicting the semantic segmentation of 5 and 10 frames in the future. We observe our model outperforms all previous work. We will now show qualitative examples of futures predicted by our model. Let's see our model in action in this intersection scene. We emphasize that this intersection was not seen in any of our training data. We pause the video right before the giveaway marking and predict different futures by sampling from the present distribution, generating segmentation, depth, and flow 2 seconds in the future. Our first sample corresponds to the car continuing straight. We sample again and get another plausible future, a left turn. The next future scenario corresponds to a right turn, and finally to stopping or giving way. Our model imagines 4 different driving maneuvers at this intersection. This example demonstrates that our model is able to learn a probabilistic embedding capable of predicting multimodal and plausible futures. Let's visualize at the bottom of the image the differential entropy of the present distribution, characterizing how unsure the model is about the future. We notice that as we approach the intersection, the network understands that the future is getting more and more diverse, which is represented through the entropy growing from low in blue to high in red. Now from this intersection, let us fast forward a few frames in the sequence and predict the future again. We now see that we only have 2 plausible scenarios, turning right and continuing straight. As we have started moving a bit towards the right, the stationary and left turn scenarios are no longer considered likely by the model. If we fast forward a little bit more, as the car is heavily engaged in the turn, we notice that the differential entropy dramatically decreases, as the model now only considers turning right as a plausible and safe course of action. Our representation also understands how to predict basic pedestrian behavior. However, there's work to be done to better represent individual instances. In the second GIF showing moving traffic, we show our representation decoding to segmentation, depth, and flow. Not the second car in the oncoming lane is occluded in the past context, but is predicted accurately in the future. Our model is also able to predict other multi-agent behavior in urban driving scenes. In the first example, our model predicts stationary traffic in front of us. In the second sample, we predict pulling away with traffic. In this example, the model predicts different behavior on a multi-lane road. The first sample shows the vehicle driving straight, and in the second, it veers around the parked vehicle before moving towards the left turning lane. This scene shows future prediction in a complex, unprotected right turn with the following possible outcomes: wait, nudge, turn right, or go straight. To conclude, we observe improvement in control performance metrics when using this future-aware representation compared to a baseline. The entropy of the present distribution can illustrate how multimodal or uncertain a scene is for our model. This is useful for understanding edge cases and when the model needs to pay more attention. Finally, we strongly advocate for end-to-end, but with finite data in compute, we need to be clever about injecting domain knowledge into our models. We do this with neural network architectural choices and auxiliary learning signals while still training end-to-end. Right now, the only structure we enforce in our latent state is perspective projection with spatial dimensions inferred from the input image. We know that perspective projection is suboptimal in many ways compared to other scene representations. We also know a lot about scene dynamics from object semantics and structure for motion, for example. There are many ways our representation could leverage these ideas to predict more accurately and further into the future. Finally, one of the hardest challenges about scaling model-based reinforcement learning systems to real-world robots is building high-dimensional dynamics models. Our future prediction model is a great start to use in an MBRM model. Further analysis will be required to understand how well the future prediction can explore and generalize into the state space, and to construct a reward model from the future latent states. Thank you very much for listening.